Now, as people started to study electromagnetic radiation more thoroughly, there were some deficiencies in this notion that electromagnetic radiation was just a series of waves. What started to happen was just started to appear as though there was a particle nature. Okay, and so what we started to figure out is that there's a wave-particle duality in electromagnetic radiation. And there were several observations that led to the understanding that electromagnetic radiation wasn't simply wave-like, but was also particle-like. So there were three key observations that helped us shape this idea that electromagnetic radiation had a particle nature to it as well. So first off, though, what is the difference between a wave and a particle? All right, so I've got a diagram here of waves and particles. Okay, so picture A, this one right here. All right, in picture A, I have a wave hitting a body of water. So what's occurring there? The wave hits the water and is refracted, okay? So it bends at a specific angle and is refracted when it hits the water. Whereas that body of water, picture B here, if a particle, all right, a pebble, which is a particle, hits the water, what we see is we don't see this refraction. We see it go down and we see it kind of curve. So what's happening there? Well, we've got increased resistance happening between all the water molecules and the other stuff in the water and our particle, our pebble, as well as we have got gravity acting upon that pebble and pulling it down. And so we're increasing the drag there because of those two components. And so we don't get a nice refraction, we get that angle. All right, now down here in C, I have a set of waves hitting a barrier. And in that barrier, you can see I've got a little tiny slit carved out of that barrier. Okay, and so what happens is the waves hit the slit, and once they come out of the slit, they expand back out. Whereas with my particle, if I beam particles at that same barrier that has a slit there, well, once my particles hit the barrier, they just fall. But if my particles hit the slit, they just keep going as though, you know, there's nothing in its way. They don't expand back out. They just keep going in that straight line in individual paths. Okay, now when we look at waves again, and we've got the those slits, okay? So my light waves hitting a barrier, I've got those slits. Now I've got more than one slit. And so what happens is my waves, as they expand back out, they start to interact with each other. And so I get in phase and out of phase things occurring. I get bright spots where we have waves in phase and dark spots where the waves are out of phase. Okay, that gives me two different types of interference. As the waves interact with each other, they're interfering with each other in one of two waves. All right, we get constructive interference. Okay, so our waves are in phase with each other. Okay, so they're in phase, all right? And so we get constructive interference where they amplify each other like that, all right? And that gives us our bright spots, okay? Whereas we also have destructive interference. Okay, our destructive interference, our waves are out of phase with each other. Okay. All right, so they're out of phase. And so instead of amplifying, they cancel each other out. And that is where we get our dark spots. All right, so when we have constructive interference, the waves are in phase with each other. They amplify each other, we get the bright spots. When we have destructive interference, the waves are out of phase. They are going to cancel each other out, and we get the dark spot. Okay? All right, so now we can go back to the story here. So we've got our electromagnetic radiation. We think it's wave-like only. But we're starting to see things that don't necessarily agree with that. Classical physics says that, well, we have this phenomenon, we can't explain it. And the first phenomenon that classical physics could not explain with electromagnetic radiation only being wave-like was what we call blackbody radiation. Okay, so basically blackbody radiation comes about when we heat objects. They give off shorter and more intense radiation as the temperature increases. So it goes like this dull red to a hotter orange to white hot. When I was a kid growing up, our burner on our stove was this metal coil. And as we heated it up, this is what we saw. It started to go a dull red, but then as it kept going, it went white hot. All right. So basically what we're seeing is that the solid object that's heated begins to emit visible light, all right? And so what happened is wave-like properties, if it was just wave-like, the wave-like properties would predict hotter temperatures. We predict these hotter temperatures would give more and more shorter and shorter wavelengths. But instead what we're getting is this weird bell curve where we get this intensity obtained with the peak at the top of the infrared visible part of the spectrum. Okay, so this led us to this dude, Max Planck, and Planck's quantum theory. So Planck understood this blackbody radiation, or he gave this theory of the blackbody radiation. And so you can see where what we're seeing is we see this bell-shaped curve where our intensities are going to peak. And so you see the dotted line here is our expected curve, all right? But what we see is the solid line. And so we see that intensity peak, we see that intensity peak, all right? And so our intensity is going to vary with the wavelength. So Planck made this radical assumption that led to an entirely new view of energy. He proposed that a hot, glowing object could emit or absorb only certain quantities of energy, all right? So, okay, so his assumption, his new view of energy, his proposition was a hot, okay, a hot glowing object, okay, could emit or absorb only certain quantities of energy. So we get this energy is equal to NH nu or NHC over lambda, okay, where N is a whole number. H is Planck's constant, okay, and then speed of light and wavelength or frequency. So if you recall to your prep courses, you should have learned that energy is quantized. All right, within an atom, we have certain quantities that we can move about through the atom. And so this quantum theory is starting to go back into that quantization of energy. We only have certain amounts of little energy packets that we can take in or emit. Okay. And so here's some pictures here of that blackbody radiation. There's our formulas. Now you notice here I don't have the N, all right? Because most of the time what we're dealing with is going to be a single quanta of energy. And we're going to talk a little bit more about quantized energy in this section, and we'll add that n back in. But for right now, we're just going to make that assumption that, all right, we're just looking at a single quantum of energy here. All right, so we've got Planck's constant. It's a 6.626 times 10 to the negative 34th joules seconds. Okay. All right, now, obviously, we're going to practice with this. Okay, so I've got a microwave oven to heat a meal. The wavelength of our radiation is 1.20 centimeters. And what's the energy of one photon? So there's that quantity 1. So 1 photon, N equals 1. Okay. So we're going to take our energy. Here, I'll go ahead and put the 1 in. So there's our 1. Here's our 6.626 times 10 to the negative 34th. We have 3.00 times 10 to the 8th meters per second, all over 1.20 times 10 to the negative 2 meters. Remember, we need to convert to meters, and we're using that E is equal to NHC over lambda. Okay? Just a matter of plugging into the calculator. We're going to get 1.66 times 10 to the negative 23rd joules. Okay. All right. So that was our first observation, that electromagnetic radiation wasn't just wave-like, but had particle-like properties as well. We have 2 more observations to take a look at to build this bigger picture.